lecture. So last time we finished with construction of CPA, secure encryption schemes. And at the end, I told you that even CPA security is not the strongest and most desirable notion for security of encryption schemes. Instead, we often want to achieve so-called CCA security, chosen ciphertext security, where an adversary not only gets access to an encryption oracle, but also to a decryption oracle. But the indistinguishability part, the indistinguishable notion stays the same. There was one obviously necessary restriction to the decryption oracle. Once you get the challenge ciphertext, you are not allowed to ask for the decryption of the challenge ciphertext. But other than that, everything's allowed. And today we want to look at a different goal in cryptography, namely authentication and the techniques, message authentication codes that achieve this. Authentication in itself is an important goal of cryptography. Message authentication codes are a very important key ingredient of many constructions. But as we will see, they also lead to CCA secure encryption schemes. The combination of CPA secure encryption schemes and message authentication codes leads to CCA secure private key encryption schemes. This is like the first application of message authentication codes, but they are important in itself. Okay, so let's first look at message authentications. So message authentication codes. So what do we want to achieve with these things? We want to achieve message authentication. And we want to also achieve integrity of messages. So that means that we want to be sure that the message that we obtain is from the source that we think it originates from and that it has not been modified. These are the two things. And then we will see today that we can construct message authentication codes that achieve authenticity and integrity from pseudorandom functions. In fact, pseudorandom functions are good message authentication codes. But if you remember it from the encryption schemes that we built from pseudorandom functions, there we first said that this gave us only fixed length message. Encryption schemes for messages of fixed length. This is somewhat similar here, and then we have to do other techniques to make sure that we also can authenticate longer messages. And finally, we will show that MAX, and as I said, MAX and CPA secure encryption schemes lead to so-called authenticated encryption, and authenticated encryption is actually CCA secure. Okay, good. This is the outline. So here is the representation of what we want to achieve with message authentication. As usual, we have, to simplify things, two communication partners, namely Alice and Bob. We have the eavesdropping Eve, and Bob in this case wants to send message M to Alice. And the question that Alice asks herself is, did Eve modify the message M that was sent by Bob, or did even Eve send the message itself pretending it came from Bob? Obviously, there's no clear distinction between the two questions, because if Eve modifies it, then you can also argue that now the modified message now originates from Eve and no longer from Bob, right? So, but often we'll distinguish the two things, and here we say that Eve tries to impersonate Bob. Okay. So this is a scenario that we are facing, and you can imagine that this is really of practical relevance. If you are talking to a website, say your bank, then you want to make sure that you're really talking to your bank and not to some imposter, right? So that you really, if you send money to people, that it's your bank that does the transaction, and you do not send money to people that you don't even know and then just want to get your money. Okay, so message authentication in itself is an important topic. It's often authentication in many applications. It's even more important than confidentiality. You don't care that people may read your messages. but you want to make sure that they come from the right source. Okay. Okay. An important other application of message authentication, obviously, software updates. If you get a software update for your computer, sometimes companies want that to be encrypted because they don't want to make their software public. But for you as a user, it's more important that it comes from the right source and doesn't include spyware, ransomware, whatever. Right? So this is maybe the currently the most important part of message authentication. So, and the means that we use in the private key setting to achieve message authentication are so-called message authentication codes, or MACs. And as usual, MACs, as I will first define the syntax of MACs, so not talk about security, but just the formal requirements for a MAC. And as often is the case, message authentication codes consists of a number of algorithms, PPT algorithms. In this case, it's again 3 PPT algorithms: the key generation algorithm, the tag generation algorithm, and the verification algorithm. So, and as usual, we also have we also have a security parameter. Okay, so the key generation algorithm, gen on input 1 to the n, and ones, outputs a key from 0, 1 to larger or equal than n. So it outputs a key whose bit length is at least n. Sometimes you can also see that it's just n. Don't worry too much about it. But here I just wanted to say it's at least n. Okay. So this is, again, as you will see, a shared key, as in the private key encryption setting. Then the tag generation algorithm MAC, on input 1 to the n, a key k here, and a message, and usually we want messages to be arbitrary bit strings. It outputs a tag, and we denote this by this symbol. And this tag generation algorithm may be a probabilistic, is allowed to be a probabilistic algorithm. Okay, so it outputs a tag. The verification algorithm, we require that it's deterministic. So the deterministic verification algorithm gets at input the security parameter, a key, a message, and a tag. And it outputs a bit b, and we denote it in this way. So here I do use this symbol. This signifies that the verification is a deterministic algorithm. So this is a fixed value. Completely determined by k, m, and the tag. And we require that for all natural numbers, for all keys generated on input 1 to the n, all messages, all tags generated as tags for m under key k, that's why it's an element. So this could be, MAC can be probabilistic, so it can generate several different MACs, tags for m and k. We have that the verification of m, t with the same key as we used to generate the tag yields 1. 1 saying we accept the tag. Okay? So that is how we use them. And again, we use the same key here, or in this requirement, we have the same key to generate and to verify tags. Okay. Now to how do we use these things? Let's say here, this was our original picture. Okay, and now what we use instead is that we have a secure channel where Alice and Bob exchange this key. Don't worry for the time being how they do that. And then instead of just sending the message m, Bob also generates the tag t and sends it over together with the message m to Alice. Okay. And the tag is supposed to prove, to verify that the message was not modified and that it originates from Bob. Okay? And that will lead to our security requirement for Max. Okay? As you can see, here I send over the message in plain. So message authentication codes, obviously, if I use them as a standalone construction, cannot provide confidentiality as well, because they just send over, you just send the message. So you want to have confidentiality and authenticity, you have to do something else. Okay? But that's the way we use these things. Okay? Now let's go back. And so as I said, often we will not be able to generate a max with message space 0, 1 star from the very beginning. Instead, we do often as an intermediate step first construct max that only can, on input, a key generated by key generation with input 1 to the n, only can tag messages of a fixed length. And this is then a fixed length MAC, what we have. So a fixed length MAC, we have key generation, tagging algorithm, verifying algorithm. We have some polynomial function, L from n to n. And then if for all n, the tag generation algorithm with a key generated on input 1 to the n only works for messages from 0, 1 to the L of n, then we say it's a fixed length MAC with message length L of n. That's exactly as in the encryption setting. Here you can easily say that it's also at most L of n, but in a construction that I'll briefly sketch, you will see that having different message length in authentication often causes a little bit of trouble. Okay, so that is fixed length message authentication codes. Okay. Good. Questions so far? So in some cases, we have also that the tagging algorithm is very simple and deterministic. But in those cases where the tagging algorithm is deterministic, which means for every m, there is just one tag. And knowing k and m, you can reproduce the tag. Right? Then there is a very simple way to verify. You get m, you get t. So you recompute the tag on the message m with the key k yourself and check whether it's identical to the tag that you received. And that is called the canonical verification, which works if the MAC is deterministic. The tagging algorithm is deterministic. If the tagging algorithm is probabilistic, this does not work, just recomputing, because you use different randomness, may lead to a different tag. Then you will reject. The verification will output 0, although it's a valid tag. So this is restricted to deterministic algorithms or deterministic MACs. But it's often the way we use these tags, or we have MACs. They are deterministic, and then we just can use the canonical verification. In fact, the construction that I will present to you, one of them is deterministic. Then we can use all these things. Okay. Yeah. And yeah, for a deterministic MAC, we only have one tag per message. Okay, so let's go to this picture again and go back to these questions. Now, given that we want to ensure that if we have a message tag pair and the tag verifies, we want to be sure that the message originates from Bob in this case and that it was not modified, right? So these are the two things. So how do we capture that in a precise mathematical security definition for message authentication codes? And notice that Eve, observing the conversation between Alice and Bob, right? And it goes both directions. I mean, if Alice wants to send a message, authenticated message to Bob, she can use the same key, right? Because it's a shared key. And they both know the MAC algorithm, they both know the tagging algorithm. So Eve can observe maybe several messages going back and forth between Alice and Bob. And of course, you want to make sure that even if she observes the conversation up to some point, Eve is not able to interject a message that was modified, right? So we have to take to account that Eve can see several tags generated by the conversation between Alice and Bob. And maybe she can even sort of induce Bob or Alice to send a specific message and a specific tag for that. And that motivates our message authentication game for MACs, and then based on that, our definition of security. So again, we use an experiment or game-based definition for security. So we start with a MAC that we have in mind, and the message authentication game for the MAC-M and between a challenger and an adversary, as usual, is defined as follows. On common input 1 to the n. So that's the only common input, the security parameter. The challenger chooses a key chosen according to the key generation algorithm. Okay. Then we allow the adversary to ask C for tags on messages of his or her choice. So she can ask the challenger for messages, for tags on messages MI, all answered with the key K chosen in the first step, but which is not given to A, obviously. And we collect those messages in the set Q. Q stands for queries. So these are the query messages. And eventually, A outputs a pair M, T. And A succeeds, and the result of the game is 1 if two things happen. Obviously, the tag verifies for M, and M was not one of the query messages. Okay? Because if that happens, then obviously A can win, right? That is like in the chosen ciphertext game, you cannot output or cannot ask for the decryption of your challenge message for a challenge ciphertext, and here you cannot simply output one of the answers that you got on the query and the answer that you get, because then you can win with probability 1. Okay? And otherwise, the result is 0. Okay? So here, the game is 1. A succeeds if A is able to produce a tag on a new message. Okay? A tag on a new message. Keep that in mind. And then we have our usual steps to define security. Finally, we write MACforge AM for the output of the game on input 1 to the n. So here's the adversary, here's the MAC. The challenger it's the same, it's just defined by the game, so we don't have to mention that. N is a security parameter, and we call the MAC advantage is the probability that A wins the game, the MAC authentication game. And that's the forging advantage of A against the MAC-M. Okay. And finally, a message authentication code is existentially unforgeable under adaptively chosen message attacks, or simply secure, if for every probabilistic polynomial time algorithm there's a negligible function such that the MAC advantage of A against M on input N is negligible as a function in N. Two things about the notation here. Adaptively chosen message attacks, well, that's because in our game we allow the messages to be chosen adaptively. So you query for the first message, you get the answer, then based on the answer you can pick your second message, get the answer. Based on the first two messages and the answers, you can pick the third message. So it's adaptively chosen. Yeah? Why is it called existentially unforgeable? Existential unforgeable because we say we don't care what the message is. The only restriction is it's not allowed in this set. Any message counts as a valid forgery if it's not in the set Q. Okay? So that's the existentially. We have put no restrictions on what kind of messages we want. Okay? I won't talk about this in this course, but there is a restricted version of security which is called selectively unforgeable, or where you eventually have to output a forgery on a message that is chosen by the challenger or that's picked uniformly at random, but at the very beginning of the game. And that is a weaker notion, but again, it's a useful notion because it's often an intermediate step to get to existential unforgery for max. Okay? So that's our game. Okay. This is kind of the standard notion for max, but in some applications, and in fact the application I will present to you, namely construction of CCA secure encryption schemes, we need a stronger notion, a somewhat stronger notion. And this goes back to what I stressed a minute ago or so. Here we require that the adversary produces a tag on a new message. Okay? The weaker notion simply says he has to compute or produce a new tag. Could be on a message that he has seen before. Okay? And so that if he gets here, say, MITI, if he's able to now compute a new tag, TI prime, on MI, which is not a successful forgery in here, then we also, in this new security notion, we call that also a success. Why that is important, it's not in the standard scenario for authentication. That doesn't really is not really necessary, but in some applications it is, and we will see that in the CCA construction it is really necessary that we achieve the stronger notion. So let's go define this, and this is called the strong forging game for message authentication codes. Setting is as before. Then the first step is as before, the challenger chooses the key. The second step is mostly the same, namely A asks for tags on adaptively chosen messages M1 through MS, but we define the set Q differently. Before we defined the set Q as just consisting of the messages that A queries. Here we collect in Q the query answer pairs. Okay, so for M1, T1, for MSTS, up to MSTS. Okay. Eventually, again, A outputs a pair M, T. And then we say that A succeeds and that the result of the game is 1 if The first condition is the same. Obviously, we want that A outputs a forgery, a valid tag on a message. But now we require that the pair m comma t is not in here. Okay? And otherwise, the result is 0. Okay? So let's just make sure that you understand this. So in the forgery game, we have m is not in Q, which consists just of these messages. Okay? Strong forgery game. We have that m comma t is not in Q, and this consists of these things here. But here, say m1 comma t1 star, if that is m comma t, is success if t1 star is not equal to t1. And it's not a success here. So here you should not be able to even modify tags. Okay? And to obtain another valid tag. I will say a few more words about this in a minute. But then we can obviously do our usual stuff. We write smacforge for output of game on input 1 to the n. We call this probability of winning the strong forgery game the MAC advantage, the strong MAC advantage. And we obviously say that it's strongly secure if for every PPT there's a negligible function such that the a strong MAC advantage as a function in n is negligible. Okay. So every success in this game, in the forgery game, is a success in this game. Because if the first component is different from all first components, then the pair is different. But a success in here is not necessarily a success here. Okay? So here the requirements for the adversary are more flexible. So this really is a stronger notion. And the requirements for the adversary are weaker. You can output more, as that counts as success. Okay? Now, there's a simple theorem that says is a MAC is secure and uses canonical verification, then M is also strongly secure. Well, if it uses canonical verification, recall that this means that the algorithm, the tagging algorithm, is deterministic, which means in particular for every M there is just one valid tag. Okay? And if there's just one valid tag, if you want to satisfy this here, you have to satisfy this here. Okay? So this notion of strong unforgeability makes only sense, or is really only different from security if you have probabilistic tagging and more than one tag per message. There's just one, you cannot modify a tag to get another valid one. Every modification gets rejected. Okay. Okay, good. And this theorem, well, just to make sure that you understand these things, it's probably an exercise or a very easy one. Okay, yeah. Again, strong unforgeability. Typically, if you just want to achieve authenticity as a standalone goal, not necessary. If you wanted to use max as an ingredient to more complicated constructions, it is sometimes necessary that you actually use strong security, as we will see. Okay. How do we construct secure max? And I will give you a construction that's secure, but it's also deterministic, so it's going to be strongly secure as well, to some extent. So the construction proceeds as follows. We construct first a secure fixed length MAC. And then we design general techniques to turn fixed length MACs into MACs for messages of arbitrary length. Well, that's similar to what we did in CPA security, first for fixed length messages using pseudorandom functions, and then we can use things like electronic codebook mode or randomized counter mode to get to the arbitrary length messages. And the first step can be achieved using pseudorandom functions. Pseudorandom functions are secure MACs. For the second step, there are many techniques known. I will present one specific one that leads to nice theoretical results, but is completely inefficient. It's probabilistic polynomial time, everything in there, but it's not used in practice because it's quite wasteful. Later, namely when we talk about signature schemes, I will present to you the currently most useful and widely used technique to go from fixed length to arbitrary length, namely the so-called hash and sign paradigm using collision-resistant hash functions. Although there are other techniques also that become more powerful in practice and more used in practice. That's due to the latest hash algorithm that has been designed, SHA-3 on Ketchuk, that gives you message authentication codes as well that don't really use collision hash and sign paradigm because they combine everything in one step, basically. Okay. The first thing we want is to construct these message authentication codes from pseudorandom functions. Okay. Do I need to recall what a pseudorandom function is? No, good. So pseudorandom functions that are not random but look like a random function. And remember, to make things concrete, to do that, we looked at keyed, efficient, and length-preserving functions from 0, 1 star to from 0, 1 star times 0, 1 star to 0, 1 star. Keyed, this part was always the key. Efficient, there is an efficient algorithm to evaluate things. Length-preserving, keys, inputs, and outputs have the same length, n, simply. Say, for some n. And given such a keyed, efficient, and length-preserving function, we define a fixed length message authentication code, MF, with message length n. As follows. Recall that on the key generation of the MAC, on input 1 to the n, it simply chooses a key uniformly at random from 0, 1 to the n. They are length preserving, so that fixes, n fixes everything. The security parameter n fixes the key length, the message length, and the output length. Then the MAC, the tagging algorithm on input a key, 0, 1 to the n, and the message also 0, 1 to the n. It's length preserving again. Outputs the tag T as we evaluate f on input k, comma m. And remember, the first input here is written as a subscript. Okay. And this is a deterministic tagging algorithm. It's a function, right? And the evaluation algorithm for that is deterministic. So it's a deterministic tagging algorithm. So for the verification, we simply use canonical verification. So the verification on input a key k in 0, 1, n, and a message m in 0, 1, n, and a tag in 0, 1, n outputs 1 if and only if t is equal to fk of m. So we compute it ourselves, compare it to what we received, check whether they are identical. That's it. That's the construction. This is not a really nice construction because first it's fixed length, and even worse, the tags are as long as the messages. But what we usually want to achieve, if you go back to this picture here, remember the example of authenticating a software update. Software updates are gigabytes. Do you want to have a tag that's as long as the software itself? Gigabytes, and then again gigabytes, and then you have to check it. That's probably going to take forever. Right? So what you typically in practice want, messages arbitrarily long, tags fixed length, 256 or 512 bits. That's it. So the tags should be much, much smaller than the messages in general. In fact, the tag length, we usually want it to be independent from the message length. Still achieving, of course, unforgeability. Okay. And this this pseudorandom construction obviously doesn't achieve that. So length is a problem, and we don't want to have these long tags. They require too much bandwidth. So that's why eventually we need to have this second step as well. But as a ingredient, the first one is good. Okay. Now is this construction secure? And theorem 4.7 tells us, yes, it's secure if f is a pseudorandom function. In the construction, I just required that it's keyed, efficient, and length preserving. That simply guarantees that it has the right syntax. This here now says if it has this additional property of being a pseudorandom, then it's also secure. And this is what we want to prove next. And the proof is nice because it is almost the same in structure, not only as a general structure that we always have, but also as the proof that pseudorandom functions lead to CPA-secure encryption schemes. Okay? Remember, we had the pseudorandom functions that lead to CPA-secure encryption schemes. To encrypt a message, we pick an R uniformly at random. and then we XOR the message with fk of r. And this proof here is almost identical. In fact, at one point, it's even simpler. But okay, let me skip this corollary first. So we need to prove so let A be a fixed but arbitrary adversary against MF. If you don't know how to start a proof in crypto, start with this sentence. Okay? This really gives you sometimes, you start thinking about a proof and you don't make any progress. And then, okay, let's start with what we really want to do. Okay, let's start with this. So just go back to the basics. Okay? So now, from a construct distinguisher D against F, right? That's our assumption. F is a pseudorandom function. Right? Then analyze running times. If A is PPT, then D must be PPT. And B, relate success probabilities. Appropriately. So what we need to be able to show is, what do I mean by appropriately? If we relate them in such a way that if D has negligible success probability, then A has also negligible success probability. And then we can argue, since D is a PPT, if A is a PPT, then this must have negligible success probability. Hence, this must have negligible success probability. Since it's fixed but arbitrary, we are done. Good. Good. And now how do we go from A to D? So we need a distinguisher. Distinguisher just gets, remember, a distinguisher for a function, pseudorandom function, just gets oracle access to a function. And then we have to analyze the success probability of the probability of the distinguisher outputting 1 if the function that it gets is a pseudorandom function versus the function that it gets is a truly random function, where the probability is over the internal choices of D and also over the choice of the function. Okay. And in the case of CPA security, what we did is just use this function that you get as input for which you get as input in the sense of query access to it, use that to construct your scheme, to answer the queries of A. And then in one case, we just have the MAC that we want. In the other case, we have a conceptual MAC, as we had in the other case where we had a conceptual encryption scheme, namely one that uses a truly random function. And here we have a MAC that replaces the pseudorandom function by a truly random function. And then we keep going. So it's really almost the same. So here is the way we get from A to the distinguisher D. So D on input, 1 to the n, and oracle access to a function f from 0, 1 to the n, from 0, 1 to the n to 0, 1 to the n. Length preserving, right? So that's the signature of our function. So we simulate A on input 1 to the n. When A asks for a tag, For a message m in 0, 1 to the m, we answer as follows. Query f to obtain f of m, and simply output the tag as the tag as f of m. So we use this f as kind of the function in our construction. When A outputs a pair m comma t, do the following: query f to obtain t hat, which is f of m, and output 1 if and only if t is equal to t hat, and A has not queried m. So in this case, I'm just using existentially unforgeability, not strong existential unforgeability. Right? This is my theorem says is secure, so not just existentially unforgeable. Okay. Distinguisher D, clear? This here, we just simulate A and then do the canonical verification, where we can use our query access to F. So if A is PPT, then D is PPT as a distinguisher. Recall that evaluating F doesn't count as a step, right? Because that it gets from outside. Oops. Okay, good. Now we want to do. I don't have that on slides. That's interesting. Okay. Now we do to do part B. We have to look at several things, but it's again very similar to the proof for the CPA security. I guess I can erase this, right? So the first thing that I can do is let's construct for f in func n. We can construct sort of a message authentication code on length n messages by doing exactly what I do here, right? Or define right? We, instead of in our construction here, we now use this f, the little f. Now the key is chosen by picking f uniformly at random, right? So key generation f is picked uniformly at random from func n. And then we do the rest as here. Okay? So instead of choosing this key, we pick f from func n uniformly at random. And for a message m, we just evaluate f of m. And then we do the thing here as well. Okay? Okay, good. Then we can do where we have two claims. And the first claim is that the MAC advantage of A against MF, input 1 to the n, minus the MAC advantage of A against M little f, n, this is the same as the difference that in probability that D on input Fk and outputs 1. Right? The distinguisher on input a random a pseudo-random part from Fk part outputs 1 minus the probability that D on input an F from func n outputs 1. Yeah. Okay. And the reason that's true is this is equal to this. If in our game here, or if you look at this, the way we do this here, if our distinguisher gets oracle access to Fk, then the way things are answered for A is exactly as in the forgery game against M capital F. Right? The keys are chosen in the right way because then we get a truly random, a random K and then Fk for that random K, and everything is answered as in the game. He plays against M capital F. And we output 1 if and only if the tag is accepted and it's not verified. So and it's a new message. So it's really as in the forgery game. And here it's also the same. If we have a truly random function, well, then it's picked uniformly at random from func n, and the queries are answered as if we were using this mac little f. So but we have to make sure that it's easy in this case, but we have to make sure that the distributions are all the right thing. Okay? First claim. Now, okay, so we know that this year is going to be some, let me make sure that I use a correct notation here. This is some function delta n. We know it's negligible. Huh? But we need to prove that this guy here is negligible. Okay. So what we is left to do is analyze this guy here. Exactly as in the other proof for the CPA security. Remember we had the repeat event and we analyzed this part here. Okay, so now what is this here? This is my second claim. I put this up here. So my second claim is that the MAC advantage of a PPTA against MF is 1 over 1 to the n. This is what we are going to prove in a second. Okay? Here, we are not talking about, it's not -1/2 or so, because here we're really talking about forgeries, not distinguishing things. Now, the theorem from the two claims. Well, we want to analyze this here, right? We want to analyze epsilon n, which is the MAC advantage of our fixed but arbitrary A against MF. Well, what I do is just, it's the MAC advantage A against MF on input n minus the MAC advantage A M little f n plus the same thing here. Right? Didn't do anything. Added 0. Now, what we can say is triangle inequality I'll just put it here, right? Okay? This here, this here is delta n, the distinguishing advantage. And this here we just upper bound it by 1 over 2 to the n. Yeah. Now we know that this here is negligible by assumption. F is pseudorandom. And this here is your favorite negligible function. And the sum of two negligible functions is negligible. So we started with a fixed but arbitrary A, constructed our distinguisher, related them, and related the success probabilities in such a way that we know that this is negligible, because we know that F is a pseudorandom function. So for every distinguisher, in particular the one that we constructed using A, is also negligible. Yep. This part you can actually, plug in CPA advantage and things like that, and nothing really changes. But now we have to obviously prove this part here. Right? And now we really have to talk about max. Okay? But even that proof now is similar to the one that we had in the CPA secure game. Can I erase this already, or do you need time? In the notes, this is claim 6, this is claim 5, by the way. Yeah, that's what I'm going to do. But we have to do it at some point. So it's really a simple application, but I want to make the structure clear, because it's nice. And it's something that we are using. Yeah, structure nice and So now we need to prove this claim that in the security game, if we use this truly random function, we have only success probability 1 over 2 to the n. Okay? And so A is still fixed. Remember, in the CPA game, I defined this special event, the event where something bad happened. Okay? Here I'm going to do a similar thing that I'm just proving now. So actually, my proof in the lecture notes, it's far too complicated, is it? So, yeah, okay, good. Let's make this. Anyway, I do it a little bit more complicated than maybe necessary, but it gives you a nice structure anyway. Okay, let's call the event how do I, valid. Okay, exactly. So valid is the event that in Mac Forge game, sorry. A outputs M, comma T with M is not in Q. Yeah. So this second condition is satisfied. Okay? Now we can analyze this MAC advantage here, which we called epsilon n. The probability of MAC Forge A against MF is 1. And now I do my usual trick. I partition this event into the two sub-events that valid occurs and valid does not occur, just to justify my lemma 3.6, by the way. Okay? So this is here the probability. Let me just do it this way here. And valid, sorry. Plus the probability of this thing here and not valid. Yeah. Valid and not valid, disjoint events that cover everything. So the probabilities are the same. Okay? Now you know what's happening next. I replace the conjunction by conditional and multiply. I can do that. It's completely in the lecture notes, so if you, but anyway. Okay. I'll do here conditioning. times the probability for valid plus the probability this thing here not valid times the probability not valid. Okay? Yeah?
Maybe a stupid question, but don't we, I mean, the probability for valid can be 0, right?
Yeah, that's what I'm going to do.
But can we then do the conditional probability?
Yeah. Right. If the probability for valid is 0, don't do the step. Go immediately to the other one, not valid, and do that. Do that as an exercise. It's nice. But it doesn't really change the proof. I just skipped this line, sort of. Okay? Okay, now now I ignore this part and I ignore this part. Okay, and then I have this. Okay? Then, and that answers somewhat your question, if not valid, then he cannot win, because that's one of the conditions of winning. So this here is 0. If you do that with a conjunction, you get immediately, well, one of the sub-events has probability 0, so the whole thing, because of the intersection of two sub-events, is 0 as well. Ignore that, period. Okay. Now we have to analyze this here, the probability for valid. Oops, sorry. I did it. Sorry, I keep that part here. Sorry, I don't want to do this. I want to do this here. Just ignore this part here, set it to 1. Yeah. This is 0. Yeah. What about this guy here? Now I know it's valid. Okay? And I have a truly random function. I have never queried f on m before. I have seen other things. What's the probability that something I output is the right value? And now you go back to lemma 3.6, which says, conditioned on all the things you have seen before, if you output something, that this is the correct function value over the choice of the random function of some particular value, function value is 1 over 2 to the n. That is lemma 3.6. So this here is really 1 over 2 to the n, and this is really lemma 3.6, as you said. But I wanted to make sure that we have to make this in this form. Okay. This is really just saying, if you haven't asked, or if you output a function value that has not been you have not seen before, that it's correct over the choice of a truly random function is 1 over 2 to the n. All function values are picked uniformly and independently at random. And that's why it's 1 over 2 to the n. Again, our image space is 0, 1 to the n, because we have Lax preserving. And that's it. Yeah.
Shouldn't be the f small f as well?
Yeah. Sorry. Yeah. This should all be, this is obviously only true for the small f. Yes, thank you. Not for the capital F. So in a nutshell, again, we prove that this construction of MAC based on a pseudo-random function is secure by just proving that if we replace the pseudo-random function by a truly random function, then it's secure. And that's the way we do prove things, the security of things that use pseudo-randomness or pseudo-random parts. Replace your pseudo-random thing by a random one, analyze that using the truly random nature of the thing, and then you're done. Usually doing this triangle inequality thing. Yeah?
I have a question. Why is the probability of not valid not, is it what? It's one, right?
Yeah, replace this by 1, sort of.
Yeah.
Upper bounded by 1, here and here.
Okay, all right.
So ignoring it simply means it replaces it by 1, yes. Okay. Yeah. Question about this proof? So if you look at these two proofs, the CPA security of the pseudo-random construction and this here, you will see that it's almost identical up to the proof of this claim, that the corresponding claim in the CPA security. We immediately get that it's also strongly secure. It's deterministic. If it's secure, it's strongly secure. Right? So this is a really nice. It's a good starting point, but as I said, it's not really practical because of the length of the tags. Okay. Now we want to get rid of the restriction. Messages and tags and keys are all the same length. Okay. So and I'll give you something to do for the break. Not that you really want that, but anyway. And I'll probably destroy a exercise, I'm not sure. But so the easiest way in encryption schemes to go from fixed length to arbitrary length is the electronic codebook mode. It's secure, but it wasn't very, very nice, right? Because if we use it with a pseudo-random function, we had to use all this randomness again and pick this randomness. So let's do the electronic MAC mode. Okay, so you have a message M in 0, 1 star, and then you partition M into parts, say M, and each Mi is in 0, 1 to the n. Yeah? Assume that it's a multiple of n. If not, do something. And I'll talk about do something is not so easy in this case. Now we MAC, or the message authentication code now with this F on M. Why don't I just do F, okay. Why don't I just do, it's a MAC of F with the same key all the time. Yep. I don't know whether that's an exercise or not. If not, good. So is that, the question is, for the break, is that a good MAC? Or we can discuss this before the break. If you have your answer right away, you are excluded for the time being. Is that a good MAC? Let's discuss it before. Just wait a second. Yeah.
I would say no, because if we send a message to the MAC
Yeah.
generation, after that we can rearrange the blocks and we can predict the output of the MAC.
Yeah. You can ask for this MAC, for this message, and then you just rearrange the blocks, rearrange the individual MACs accordingly. Forgery. Right? So if we want to do something like that, we have to make sure that rearranging things is not possible. Yeah? Okay. And also, okay, now I want to extend this MAC from the fixed length MAC. So far I said it's n. Okay. Now let's do, well, why not doing it for less than or equal to m? And so if I have a message m in 0, 1, say L, and L is strictly less than n, then I do the message m prime, which is simply m, and then I concatenate zeros. How many n minus L? Zeros? Huh? And the MAC for m under the chosen key, I don't denote this, is simply the MAC for m prime. Is that a good idea? Now your message space is now 0, 1 less than or equal to n. Right? And you can output any message that you did not query with the tag of length up to n. Yes?
We can make a forgery for m and just concatenate 1, 0.
For example, if you have that, you get the message m, you get the forgery for m. Well, output m prime itself. Since L is less than n, m prime is not equal to m, but the tag for m is a valid tag for m prime by construction. Yeah? So concatenating is not so easy in authentication things. In encryption, that usually doesn't cost too much. You have to be a little bit careful, but here it's really difficult. It's much more difficult in general. If you went to the introduction to crypto course or something like that, or you have ever heard something about the Merkle-Darmstadt construction, then you know that this is one of the things that makes life there a little bit more complicated. So we want to, so even when I said here, well, it's all in 0, 1 to the n, the rearranging is a problem, the concatenating with zeros, filling up with zeros is a problem. So, so it's not so easy. In fact, I'll give you a construction later on that avoids both of these problems. but I won't give you the complete proof for it. It's a mess, actually. Okay, but with that, but think about these examples. So this is really not so easy. So we take, let's do a 30-minute break up to 9:50. Okay. Any questions about this here? You understand this, and you will understand why the following construction is a little bit more complicated than maybe what you would have expected it to be. So we want to go from fixed length to arbitrary length. It's not a practical construction, but it's one that it is one that works. Okay, so assume we have a fixed length MAC with message length n, say, as the one that we constructed before. Now we construct the new MAC as follows for arbitrary length messages. Okay. The key gen algorithm is as the previous one. So we really use the same keys, just pick one key and use that again and again. And we also want to partition these things into blocks, but we do it differently than I said there. So the MAC, the tagging algorithm, gets as input the key 0, 1 to the n, and a message of length L, which is at most 2 to the n divided by 4. So it doesn't seem to be one for arbitrary length messages, but now we go from message length n to message length 2 to the n divided by 4. So exponentially large in n. Okay, so it's much longer. Okay, you see why I need that restriction. Okay. And we parse m as a block of length, in blocks of length n divided by 4. Okay. And if it's not of length n divided by 4, multiple of n divided by 4, we'll have to do something. Okay, it's not so easy. So the second problem is a little bit, I'll say something about this later. Okay, now to compute the MAC, we choose a random value in 0, 1 to the n divided by 4. Okay, so it's a probabilistic tagging algorithm. And we compute Ti for I from 1 to d. D is the number of blocks in our message of length n divided by 4 as a MAC under key k of our original scheme as R concatenated L concatenated I, where I is the index, concatenated Mi. Okay. So first we have to make sure that everything that this is of length at most n, or exactly n. Okay. So notice nr is of length n divided by 4. Yeah? L, we include the length of the message. Okay. But the length of the message is below 2 to the n divided by 4. And everything up to 2 to the n divided by 4 minus 1 can be represented as a bit string of length n divided by 4 with leading zeros if necessary. Okay? Yeah? So it's 2 to the n. I assume that 4 divides n, right? Okay. Anyway. So we can represent this number with exactly n divided by 4 bits. So L is of length n divided by 4 as well. I is here, the index I is between 1 and d. Okay, d is also smaller than n divided 2 to the n divided by 4. We can represent it again with n divided by 4 bits. If necessary, leading zeros. Okay? And then we have n divided by 4 bits in Mi itself. Okay? Good. So, and the overall tag now is RT1 up to TD. Still, if you look at it, it's too long, right? Because each block now gets a tag, each block of length n divided by 4 gets a tag of length n. So we don't solve our problem that we want short tags. But we do solve sort of the problem that we can now tag much longer messages. Okay? Let me explain some of the things in here. The R is necessary. I don't want to talk about this. Why is the I now, why do we include the I? That prevents this stuff here, rearranging. Okay? Because if you rearrange, things get a different position, and the O tag no longer works. If you move here, if you move, assume S is 2, you move M1 to position 2, it gets now in position 2, M2, for which you do not have the tag. The R is you don't want to, okay, let me explain why you want you have to include the R. The R is there if you have 2 of those things. Yeah? Here, then you could just keep things in the position, but mix the 2 tags. Right? If I had here M1, M2, and M1 prime, M2 prime, I could do M1, M2 prime, M1 prime, M2. So they stay in the same position, but I can mix them. Okay? This R prevents the mixing, right, with high probability. So R prevents mixing from 2 different things. The I prevents rearranging in one thing. Okay? The L, now you can really simply fill up. Because if you fill it up with zeros, the length gets different. If I do now M and M prime has a different length than M. So since I include the length, this here no longer works. Okay? So with these 3 things here, we exclude sort of the easiest possible attacks on the electronic Mac book, sort of Mac, electronic Mac mode. Right? So R, not mixing between 2 things. It has a different R and that they will not fit together. The L, you can fill up things with zeros, and the I, you cannot mix within stuff. And that already suffices to prove that this thing here is secure. Let me do this here. So if M prime is secure, then the new one is secure. If it's strongly secure, then the other one is strongly secure as well. By the way, the verification is because I give you R here, the randomness, you can again do something like canonical verification. Just do it on each block, right? It's all there. These values, the indices, I, the length, L, you can all compute from the M. The R is given to you, so you just do something similar to canonical verification on each block. Yep. So So the proof is a little bit weird, but anyway. So as I said, we want, why is it good enough to have length 2 to the n divided by 4? It's a funny reason. For longer messages, do whatever you like. I don't care. Why? Output 0 as a tag for everything that's too long. That's longer than, that has more than 2 to the n divided by 4 bits. Why can you do that? Yeah?
Because an adversary can never generate such a message.
Exactly. A polynomial time adversary in n cannot output a message in polynomial time of length 2 to the n divided by 4. So we don't care. So that's a theoretical reason. It's a good theoretical reason. A practical reason, assume that n is 500. Then 2 to the n divided by 4 is, okay, let's do 2,000, n divided by 2,000. Then 2 to the 500 exceeds the number of atoms in the universe. So you probably agree that an adversary will not be able to output a message of this length, exceeding the number of atoms in the universe. So we just, if we can do things for messages that are just exponentially long up to some exponential length, then we are done. Okay. Okay. Yeah. So this is what I said here. Okay. So I forgot. So the three on this here, 3 different easy attacks, and this thing avoids all of them, and that already is enough to prove that it's secure. Okay. So now we have seen authentication codes, message authentication codes. We've seen that we can construct them from pseudorandom generators. We have seen again a proof for construction that's based on pseudorandomness. The security proof replaces pseudorandomness by randomness. Analyze the random stuff, and you're done. We'll come back to authentication, and in particular, we'll also come back to authentication. Yeah, we come back to authentication later in the course. We talk about hash then sign and other similar things. Okay. Question to this part? Then I would like to move on. Now we go back to our to encryption and encrypting things. And also a little bit staying at the authentication part. Because so sometimes you want to achieve just confidentiality. Sometimes you want to achieve just authenticity. But in many applications, you want to achieve confidentiality and authenticity. If you send your bank account information somewhere or get things, you probably want to have things confidential and authenticated. So you want to do both. You want to achieve both goals simultaneously. We have techniques for the individual tasks. Now, how do we combine these techniques to get something that achieves confidentiality and authenticity? Okay. And there are several ways to achieve that. Well, so you want to achieve confidentiality, you want to achieve authenticity. So the first thing is, say, you could try encrypt and then authenticate. Okay? So what you do, you have an encryption scheme and you have a MAC. For the encryption scheme, you have a key KE. For the MAC, you have a key KM. Now, the encrypt and authenticate is you encrypt the message and then you tag the message and output C, T. Encrypt and authenticate. So do the things really separately, individually. The second thing that you can do is authenticate, then encrypt. So you first compute the tag, and then you encrypt the concatenation of the message and the tag. And the third way to combine the two things is encrypt, then authenticate. You first compute the ciphertext using your encryption scheme, then you tag the ciphertext, not the message, and then again output C, T. So here it's only C, in the other two cases it's C, T. Okay. What about the three things? Let's start with the first one. What do you think about the first one? There is no specific argument against it, but there is a general argument against it. You compute the tag on the plain message. Message authentication codes are not meant to guarantee confidentiality, which means the tag may well tell you some information about the message. It's not meant to achieve confidentiality. So this part, yeah, achieves confidentiality. But this part here, which is included, and you want to have confidentiality and authenticity for the combination. But T, I could easily design good MACs that tell you something about the message. Which is not very nice. The pseudo-random construction doesn't do that, by the way. But in general, it's not a foolproof thing to do. And in fact, if you already have that the tags also provide confidentiality, that they could do probably something easier than encrypt then and authenticate. This thing here, that is something you do in the exercises and tutorials. I think you discussed this. There are specific combinations of a secure encryption scheme and a secure MAC scheme where authenticate then encrypt is not secure. Again, you get additional you have to take account that you get additional information. Something else is included in this stuff. This one here, encrypt then authenticate, is the right thing to do. This is the foolproof thing to do. By the way, don't get me wrong, this is not necessarily insecure. In fact, in SSL and in early versions of TLS, this is the thing that was recommended. Not recommended, but it was allowed to do that. And if you combine the things carefully, it works. But what we usually want to achieve are constructions that are as foolproof as possible. And this thing is. Encrypt and authenticate. Really, if you can, as we will see, you can combine any CPA secure encryption scheme, any secure authentication scheme, and it still has the properties that you want. In fact, you even get, if you do that, CCA secure encryption. So even stronger security for the encryption. And we want to look at these things in more detail. Okay. So here, and the encrypt and authenticate part is secure for all CPA secure encryption schemes and strongly secure MACs. For those things, we now really need strongly secure MACs because we look at this combination. So so far, I always said we want to encrypt messages of arbitrary length. Message space is 0, 1 star. Okay? But what we usually have is if we want to achieve like CCA security or encrypt and authenticate security, messages will have a certain format. And if the decryption algorithm realizes that the format is not right, or it even realizes that the ciphertext doesn't have a correct format, then it should not output a message or something, it should just output a reject symbol. I will do that in this way, just output a reject symbol. If you implement these things, the more secure thing is probably not to output a reject symbol, but send random stuff back. Don't even tell the other guy that something was wrong. Just send him something that's completely useless. Okay, so that is what I recall by what I mean by rejecting ciphertext. So formally, we no longer, in particular, the verification algorithm now has 3 possible outputs. 1, 0, and reject. Or often simply 1 and reject, or this reject symbol. Yeah? Okay. Good. So now let's move on to this, or make this encrypt and authenticate more formal. Yeah? And also tell you what the decryption algorithm does. Because so far I only talked about encrypting stuff. So let pi be an encryption scheme, and so encryption algorithm, decryption algorithm, and the key generation algorithm gets this subscript E because it's for the encryption part. And we have also a message authentication code, MAC and verify, and the key generation algorithm gets the subscript M. And now we define an encryption scheme pi prime consisting of gen prime, enc prime, and dec prime as follows. On input 1 to the n, the key generation algorithm now picks a key for the encryption scheme and a key for the message authentication code. And the key is the combination of the 2 keys, KE, KM. On input 1 to the n, and the key consisting of key KE and KM and a message M, compute the ciphertext as follows. We first, using key KE with message M, compute C. Then we authenticate the ciphertext with the key KM, compute T, and we output the pair C, T. This is C, T is now the ciphertext combination. The decryption on input 1 to the n, the key consisting of KE and KM and the ciphertext C, T. We first verify that T is a valid tag under C, for C, for the ciphertext. If yes, then we output the decryption of C under key KE, otherwise we output reject. We authenticate the ciphertext and check that the authentication is correct. Now, depending on whether the pi and m work on messages of fixed length or arbitrary length, you have any combination you like. Right? Let's assume for the simplicity that they all work on 0, 1 star. Good. So we want to show that this is CPA secure and it's strongly secure, and that it's still strongly secure as a MAC. But what I really want to do is the following. So we will define something that's called an authenticated encryption scheme, where you cannot forge ciphertext, which means even if you see ciphertext, you cannot create a new ciphertext that will not lead to rejection in the decryption algorithm. Okay. And then we will show that if we have an authenticated encryption scheme, then it's actually CCA secure. The reason is, the intuitive reason is, if you cannot create new ciphertexts, right, as an adversary, your decryption oracle is useless, because it will always, you produce a new ciphertext, and the decryption oracle will answer with reject, 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 reject. You can give this answer yourself. So and then you are, okay, if the encryption scheme is CPA secure, we cannot produce new ciphertext, then it should be CCA secure. And that's actually the thing that we do, and then we actually get that we have a CCA secure encryption scheme. Okay. So, but first we want to have this authenticated encryption, and we want to argue what that, want to define it, and then say why that leads to CCA secure encryption schemes. The first notion that we introduce is the notion of unforgeable encryptions. We cannot produce new ciphertexts. It's sort of it's just transforming existential unforgeability to a space of ciphertext. That's all we do. So we have an encryption scheme pi, and we have a challenger C and an adversary A, and the unforgeable encryption game for A, pi, and on input n is as follows. Now we're talking about some encryption scheme, but always have the one that I described before, 5.1, in the back of your mind, the one with encrypt and authenticate. But here I'm not talking about encrypt and authenticate, I'm just talking about any encryption scheme. So on common input 1 to the n, in this game, the challenger chooses a key uniformly at random with input 1 to the n. Then A asks C for encryptions of adaptively chosen plaintext M1 through MS, and CJ is the answer, MJ. And in the set Q, we collect the answers with CJs. Okay? Not the messages, but the ciphertext that we received. And eventually A outputs a ciphertext C. And let M be the decryption of C, which may well be a reject symbol. And then the result of the game is 1, so A wins if M, so C is a ciphertext that decrypts to something that's not reject. And C is not in Q. Otherwise, the result is 0. So the goal of the game is for the adversary to construct a new ciphertext, namely one that was not obtained by his queries, and that decrypts to a message that's not just reject. Okay? But from the syntax, this is very similar to the unforgeability game, right? Except that here we do not include the M's in here, but the C's. Here is not a MAC algorithm, a tagging algorithm, it's the encryption algorithm. And here we have, accordingly, we have changed things a little bit. This sort of corresponds to the tag is accepted. This here is like, no, we get something new. And we write angforge AMN for the output of game on input. This should be a pi, not an M. This should be pi on input 1 to the n. And as usual, as you will expect, the encryption scheme pi has unforgeable encryptions or is unforgeable if for every PPT A there is a negligible function such that the success probability is a negligible function in n. Okay. Yeah. The schemes that we have seen so far, except this encrypt then authenticate, do not have unforgeable encryptions. I mean, if you look at the one-time pad, every bit string is a valid ciphertext. If you look at the pseudorandom construction that we had, every combination is a valid ciphertext, basically. If you look at the pseudorandom construction, everything is a valid ciphertext. So they all violate this definition. Okay, so now we call an encryption scheme an authenticated encryption scheme if it's CPA secure and it's unforgeable. So it must be CPA secure and unforgeable. And then it's called authenticated encryption. This is just an intermediate notion that we all use to do something more interesting. In fact, what we'll prove is theorem which I already mentioned. If pi is CPA secure and M is strongly secure, then the construction 5.1, the encrypt and authenticate, is an authenticated encryption scheme. Then we also have, if an encryption scheme is an authenticated encryption scheme, then it's CCA secure, with the intuition that I already gave you. If it is an authenticated encryption scheme, it's CPA secure, but you cannot produce new ciphertexts, so the decryption oracle is useless to you, and because it's CPA secure, then it's really CCA secure already. And as corollary, you get that if pi is CPA secure and M is strongly secure, then pi prime as in construction 5.1 is CCA secure. We know that it is an authenticated encryption scheme. Every authenticated encryption scheme is CCA secure, hence it must be CCA secure. Good. Now let's look at theorem 5.4. So we want to show that our construction 5.1, encrypt and authenticate, is an authenticated encryption scheme. So we need to prove two things. We need to prove it's CPA secure, and we need to prove that it's unforgeable. The CPA security is an exercise. And it's not as simple as it looks. You may think, well, I mean, I start out with a CPA secure encryption scheme. Well, then pi prime should be CPA secure, right? That's not quite true, because ciphertexts in pi prime have a different structure than ciphertext in pi. You get the additional information that's included in the tag. We may have to show that the additional information that's included in the tag doesn't destroy CPA security. Right? Ciphertexts now are C from the CPA secure encryption scheme plus tags. And the tags may well destroy the CPA security. This says no. But there is something to prove. The forgeability I will do here. And it's I'll do that in particular because it's the first time where we see that we combine two primitives to something new. Right? And that we have to prove properties that are based on both and have to reduce them to the individual things. And the technique is quite simple, but it's in sort of a new little thing in our toolbox. So we want to prove this here. And so what we'll do, we start out from a ciphertext forger to a MAC forger. Right? A ciphertext forger in our construction 5.1, the encrypt and authenticate, and from that we construct a MAC forger against the original MAC. Okay? And then, as usual, we'll say if this is PPT, then this is PPT. We relate the success probabilities of the two, and then we know that this is negligible because we know that the original MAC was strongly secure. And then this here must also be negligible because we related the two functions in such a way that if one is negligible, then the other is negligible as well. Yeah? And here, what we do is A plays the role of the challenger for A prime in the unforgeability encryption game. So we construct A from A prime, and we do that by A playing also the challenger for A prime. And that in particular includes that A must answer the encryption queries of A prime, because A prime is an adversary in the unforgeability encryption game, and it may ask for encryptions, which in the original game are answered by the challenger. But now A plays the challenger for A prime, and hence it must answer these things itself, using its own challenger. And that's what we have to do. I will give you a picture for this, and then this will be the same. And what we have is the distribution of the answers to A prime must be as with the real challenger, because otherwise we cannot realize the relevant probabilities. Before, let me go directly to this here, to this picture here. Okay. So what we have here is here we have our A. This is going to be the MAC forger. Yeah? That can use this A prime, which is the encryption forger. A has its challenger, because we look at a MAC forger which has its challenger, right? But this guy here runs inside A prime, so it must run it and it must provide the answers to A prime. Maybe using its own challenger, but it must provide the answers for A prime. So in the MAC forging game, the challenger constructs the key that that the adversary wants to attack, right? This KM. Yeah? And the challenger will also answer the tagging queries of A. Now, to define A, the first step of A, it generates a key for the encryption scheme itself. Okay? Because it's just an adversary against the MAC thing, the MAC system. So it gets a key for that thing from the challenger. Well, the challenger has that. It doesn't give it to the adversary, but it has it in mind. So the A that wants to use A prime, which is an encryption forger, it generates sort of the second part of the key itself. Okay? Now the A prime is against our encrypt then authenticate. So for it, things have always two keys, the encryption scheme and the MAC scheme, the key. So then after it has done so, it gives obviously this one to the end to A prime. Now it simulates A prime. Yeah? Now A prime is an encryption forger. It will ask for the encryption of messages MI. Yeah? Okay, good. So A prime sends an MI. Now A has to play the challenger for A prime. So what it does, because it generated the key itself, it can at least compute the ciphertext under the original encryption scheme itself. It has a key. It has it generated itself. Okay? So the CI it can generate itself. But A prime expects ciphertext tag pairs as new ciphertext. So to get the tag on this here, A can use its challenger, because that will answer tagging queries. So it sends the CI over to its challenger, receiving back the TI, and gives that pair to A prime. So that's the way it answers the encryption queries of A prime. Partially, it can answer them itself, or can construct parts of the answer since it has generated the key for the encryption part itself. The tagging part it answers by or computes by using its challenger. Eventually, this guy will output a pair C, T, and that is the forgery that A outputs to its challenger. Okay. Good, so the first thing that we'll have to check is that if A prime is PPT, then A is PPT. Yeah. Key generation is a probabilistic polynomial time algorithm. That step works. Running A is PPT. Computing the encryption algorithm is PPT. We can do that. This here we get back in one step, sending it over, PPT, doing this here, PPT. So the whole thing is a PPT. So if A is a PPT, then A prime is a PPT, then A is also a PPT. Okay? And finally, what we want to prove is that the MAC-Forge advantage of A against M is the same as the encryption forge of A prime against our pi prime on input N. This is our claim. Oops, I forgot the probabilities in front, sorry. And I should say this is a claim. Okay. This is what we need to show. Okay? Okay. So first of all, let's convince ourselves that all these things, the CIs, TIs, are generated as in the real game for A prime, the real encryption forgery game for A prime. The key here is generated as in the real game by C. This here is chosen as in the real game by A itself. So the combination is chosen as in the real game. The key generation for pi prime is choose from the key for E, choose a key for M, or pi and M. This is what we've done using the corresponding key generation algorithm. So A prime chooses or plays the game, the unforgeability, encryption unforgeability game with the keys as generated in the game. The answers for the queries it poses are answered correctly, right, as in the game. This is a real the real ciphertext under pi. This is a real tag under M, and you get the message back. Good. So A prime behaves as in the real game, although it now plays not against the challenger, but in this combination. So everything's okay. So what we can say is that the probability that C comma T is a valid forgery is as in the game of A prime in the Eng forgery game. Yeah? Good. So the probability that A prime here, the simulated A prime outputs a valid tag combination of C and T is as in the real game. Now I claim that if A prime succeeds, then A succeeds. So if A prime is successful, then A is successful as well. And why is that? First of all, it will verify correctly. So everything is, so we need to make sure that here that it will decrypt correctly, or that the tag will be accepted. Right? But since we assume that A prime succeeds, we are in the case that it succeeds, well, this will be okay. Now we need to make sure that C is not in Q. Okay, oops, why is it not working? So why is C not in Q? So in here, these are now the CTs, right? So we have to make sure that CT is not equal to any of the CITIs. Okay? Okay. So for all I C, T is not equal to CI, TI. Because these are now the new encryptions. These are the encryptions, the ciphertext for pi prime. Okay? Yeah. But that's exactly because of strong unforgeability. Now we use strong unforgeability. And would not be good enough to just have unforgeability, because that would not be good enough. Okay. Because of strong unforgeability, we have that this is different from all the things that we put into Q. And that's it. So then we really have that this guy wins exactly if the simulated A and wins, and the simulated A prime wins with the same probability as A prime in its real game. And that's it. And here, as I said, we use strong unforgeability to achieve that. The interesting thing, the new technique that we saw in this security proof is here, at this point. We need to attack a component of a scheme using an attack on a more general scheme. And that implies in particular that we play against only partially defined keys. So what we do as an adversary with the rest of the keys we generate ourselves. And that gives us also the power to do some of the things that normally would do the challenger for this guy, we can do it. And we have to complement that with the answers that we get from our own challenger. Right? So we have a combined scheme here that for the first time we saw something that is a combination of two things that we already know is secure. Now we have to reduce the security of the combined scheme to the individual parts. And that often implies something like this, using these keys. If you do advanced stuff, you sometimes don't generate it as prescribed, but slightly differently. So that you can cheat without being caught. And you will never want to get caught. Okay, so this is important that you realize this, why we do this, why we can do this, and what's the goal behind this. So this was our first part, the first proof, combination of things, proving the security of a combination of things. This will happen several times in the course, and they all look similar to this. Okay, next time I will really prove this thing here, theorem 5.5, and there I will also use a technique that I used before, but I make it explicit there, namely the difference lemma. There I really state it, explain it, and use it. So it's another technique that we use, but then we are almost done with our techniques. Okay, that's it for today. By the way, next week I have to travel around, or I have to finish around 10:15 because I have to travel somewhere. I will just do the course without a break until 10:15 or something like that. Okay, good. Thank you. See you next week.